Okay, we're going to talk about history of the and models of the atom today, which is, sorry, Unit 2 here, periodic table. So this is actually the last page of your notes. You have this whole thing. So we're going to talk through it and just kind of go piece by piece how we go from Democritus in BC to the present day version of the atom that we know and love. So the idea of an atom, which means unable to be divided, goes all the way back to BC and a Greek philosopher named Democritus. And he came with this idea that water and iron and all these different substances were made up these discrete units called atoms. And each one had its own individual type of atom. And obviously, we know today that like water is made up of hydrogen and oxygen atoms, right? And that's different than iron, which is an element, which is made up of one type of atom. So we have compounds and elements. Before it was just one type of thing that made up each item that we know on Earth. And then in the 1800s, so for a long time, that was kind of what we went with. And then in the 1800s, John Dalton developed this atomic theory, but his was basically the same thing as Democritus, but it had scientific theory behind it, or scientific evidence. And he came up with this piece that reactions happen in whole number ratios. So example, 4 to 2 would give you 2 products or whatever it might be, which means your atoms cannot be divided. So plum pudding model was the next development, and this was by J.J. Thomson. And he said that, well, in our atom, we actually have these negatively charged electrons that are floating around in this positively charged, like goo kind of thing. And the reason why is because it was plum pudding. So as we'll see next, there's this gold foil experiment. And if this was the case, then you'd expect these alpha particles to just go right through a sheet of gold foil. But as we see with the Rutherford model, is that the electrons, many of them went straight through, but many of them also bounced off. So you get these arrows going in all these directions of alpha particles, or a spreading of that ray. And what that showed us is that we have a dense positively charged nucleus in the center of an atom. So experimentation here is what's changing our knowledge and our understanding. And again, this is just reiteration. You don't have to redo that. But again, if there was no nucleus, we would expect it to just go straight through. But if there was a nucleus, we get the bouncing off, which is what we see. So the next development came in 1913, where Bohr, different from his predecessors, predicted that the electrons were outside of the atom. Okay, so he predicted that electrons were outside of the atom. And he had them in set paths that he called orbits, just like planets orbit the sun. But in his version of these rings, these distinct energy levels, is where the modern version tends to deviate. But the nucleus is still part of his. He just has these distinct rings called orbitals. And we're actually going to draw some Bohr models because it is a helpful way for us to understand on a very simple level what electrons are like, because there are some positives to the electrons here. So now we describe orbitals differently because they have different shapes and the electrons tend to move freely. So instead of these rings, you have these like lobes, where imagine it's like a balloon shape and the electron's somewhere in there. Imagine you had a balloon and like you put a quarter in it and you shake the balloon, the quarter is going to fly around everywhere on the inside of the orbital. And that's basically what the electrons do today. So, and you don't have to write anything here, but in these orbitals, we have spheres, dumbbells, flower shapes, and so forth. These are the different orbital shapes that we see. A couple things to note is that we can't figure out exactly where an electron is. We can't figure out its location, direction, and speed all at the same time. But what we can do is predict and say that it's somewhere within this sphere. And these are 3-dimensional shapes, not just 2-dimensional shapes. But they still have energy levels like Bohr predicted. And then the number depends on the number of electrons, the orbital shape and type. And this is what our periodic table looks like as well, because the first 2 columns are all these types. The last 6 columns are all this type. The transition metals all have these D types. And then our F types are for our lanthanide and actinide metals. So the different orbitals still correspond with the shape of the periodic table that we know today, which is what we learned last week. So big idea here is that the outer rings, or we'll think of them as rings because it's distinct energy levels, the outside most orbitals are what we call valence electrons. So in a Bohr model, the first shell only gets 2 because if we look at a periodic table, we only have hydrogen and helium. Second shell has 8 because we have 8 electrons. And then it gets kind of weird in the third, because in the third row of the periodic table, from sodium over to argon, we only have 8 elements, but then later we can add 10 to it as well. So Bohr's model wasn't perfect in predicting certain aspects of chemistry that we know. And that's why his model has been faded. But it is helpful for us to realize the basic shape of an atom. And then lastly, valence electrons, as we know, are found in the outermost shell. And everything in the first column has 1s. That's why those alkali metals plus hydrogen all have 1 valence electron. That's why they're grouped together. Beryllium through barium, same thing. They all have 2. All of my transition metals have 2 as well. And then I get to the other side of the periodic table where boron is, and I have 3, 4, 5, 6, 7, and noble gases have 8 valence electrons with the exception of helium. But because helium's in the first row, the first shell only gets 2 electrons. Okay. And then, in that electron configuration, you imagine your hydrogen and, or let's say fluorine, right? If you have 7 valence electrons, if I get 1 more, I get 8, just like neon would have, and that's actually really stable. So atoms that form ions, either a positively charged cation or a negatively charged anion, that happens so that they can get a full shell of electrons. And that's why chemical reactions occur. So if we look here at a cation, we have more protons than electrons, so it's a positive charge. And anion, like fluorine would form, you have more electrons than protons, so you get a negatively charged atom. So going back to this, realize that our through experimentation, our knowledge of what an atom or what matter is made out of has grown from discrete, random, or like whole objects called atoms to this very complex nucleus with complex orbital shapes that we know today. And our understanding will continue to grow and develop over time. And that's the point. Just because we have a scientific law or for scientific theory doesn't mean that they're incapable of change, but they are all based off of, from Unit 1, experimentation and data. So the next thing is we're just going to get a sense for the construction of an atom. And we're only going to go to the third orbital in these Bohr models. So the first orbital holds 2, second holds 8, and every after we'll say holds 18. But we'll say 18 or less. Remember, atomic number is number of electrons and protons. But we're going to go through a few examples. So carbon, if I were to look at the periodic table, its atomic number is 6, which means that it has 6 protons. It also has 6 electrons. So my first electron will go in that shell. My second electron will go in the shell as well, leaving me with 4. And then after that, carbon has 1, 2, 3, 4 electrons in that next shell for a total of 6, because that's its atomic number. Now, carbon's atomic mass on the periodic table is 12.01. When we round it to the nearest whole, it has a mass number of 12. If I subtract the number of protons from that, I get my number of neutrons, which is also 6. And remember, protons and neutrons, when we add them together, we get the mass of an object, our mass number. Okay? Protons and neutrons minus protons gives me neutrons, and that's what we're figuring out here. Okay? So in your homework, we have 4 examples. We're going to do the first ones together, the first 2, and then I'll let you try them. So nitrogen's atomic number is 7, so I know I have 7 protons, and I know I have 7 electrons, so I got to fill it in. 1, 2, and then my next one's going to have 5 electrons. 1, 2, 3, 4. And they don't have to be perfectly spaced, 5. So a total of 7. And then neutrons, what I have to do is take my mass and round to the nearest whole, which is 14, and subtract protons 7 to give me 7 neutrons. So some of these lighter elements have the same number of protons, neutrons, and electrons. And for our case, we're going to assume that every atom is neutral. Okay, so let's go to the next one. So lithium, atomic number, tells me that I have 3 protons and 3 electrons. So that part should be pretty straightforward. Atomic mass is 6.94. So to find neutrons, I have to round to the nearest whole, which would be 7. I subtract protons 3, and I get 4 neutrons. Okay, so I have 3 protons, 4 neutrons, and then 1, 2 electrons in the first shell, and 1 beyond it, and so forth. Now, if I were to ask you to identify this element, you could just count the electrons, 1, 2, 3, the number of protons, 3, and then figure out that it is lithium. So I want you to pause the video here and try phosphorus and try the last one, helium, as well, and then we'll go over them together. All right, so protons here, oops, sorry, I'll do it over here first. 15 protons, 15 electrons. Okay, so placing those electrons might take a little while. But then atomic mass, I got to round it, so it's 31 minus number of protons, which is 15, gives me 16 neutrons. So I have 15 protons, I have 16 neutrons, and then count them. 2 electrons in my first shell. My next shell can hold 8, so that'll give me 10. So I'm just going to place the 8, 2, 3, 4, 5, 6, 7, 8. Then I have 5 left in my third shell. 1, 2, 3, 4, 5. Nice thing about this is I could say how many valence electrons does phosphorus have, and you just count them in the outer shell. It'd be 5. Lastly, helium, atomic number is 2, so it's 2 protons, 2 electrons. Atomic mass is 4.00 and some change. So rounded to the nearest whole is 4 minus 2 gives me 2. It has 2 protons, 2 neutrons, and 2 electrons as well. Helium, a noble gas, has a full outer shell. Even though it's that first shell, it's full. So it's not very reactive, just like all the noble gases are. Versus if I looked at phosphorus, it'd have 1, 2, 3 open spots. So it's going to add 3 electrons to give me a -3 charge, an anion. If I look at lithium, it has 7 empty spots in this shell. So it's actually what it's going to do is it's going to get rid of that 1 electron to form a +1 charge. And if I were to look at nitrogen, just like phosphorus, it has 1, 2, 3 open spots, so it'll form a -3 charge when it adds 3 electrons. And if you look at the periodic table, you can actually see nitrogen's right above phosphorus. They both have 5 valence electrons, and they both form -3 charges. These guys have 6, so they form -2, -1, and 0. These guys have 1 valence electron, they'll get rid of it to form +1 and +2. And right here, most of these are going to form a +3 as well. So the valence electrons are directly related to the charges that atoms form as well. So all this stuff works together. And again, our understanding here is what allows us to understand the basic principles of chemical reactions and the way that the world works, the physical and chemical properties that an object has as well. All right, guys, love you, appreciate you. Let me know if you have questions. Make sure you submit your notes now. Have a great day. Bye.